Okay. Well, hello, everyone, and thank you very much for an informative session. It's been an enlightening morning, and I want to take you in a different directions than what people have been talking around. Over the last 3 years, I was tasked at the University of Southampton to set up a new department in chemical engineering, and I based the chemical engineering department around sustainability, and we built a very successful system on sustainability. We have over 100 students, and the course has just been nominated by the Times Higher Education as number 4 in the UK out of 30 chemical engineering departments, and we've achieved accreditation. And the second phase of implementing sustainability at the university is to start building a research endeavor around it, or a research center. So my approach has been to integrate the chemical approach through the system. Okay, so we've all know what sustainable development are. We are familiar with the goals and the development of the goals, but my focus has been is how can we effectively implement sustainable development in chemical engineering sector. And for us to do this, we need to actually go back to the step of what is chemical engineering and then build an endeavor around it. Chemical engineering is revolving around the sustainability of raw materials to be upscaled, and then once you upscale the raw material, you process it through the reactive systems to generate the useful products, but you have waste. So you need to think of the separations. I need to think of the holistic processing element behind it. So before we move on to the chemical engineering aspects, we go into sustainability and break it down into its base elements, and it revolves around the 3 components, as we refer to it, is the profit, the people, and the planet, or biosphere, society and economy, with SDG 17 being the partnership, the stem that threads everything together. And the concept that we are trying to establish here is to meet the SDGs through the manufacturing of chemicals and goods everywhere. So the first element of our research endeavor here is to understand that SDG is a complex system, and there need to be an advanced decision-making tool to actually integrate everything. And this encompasses the fundamentals of sciences to the advancement of engineering and build up the system through it here. And it has to be approached in a systematic point of view. So we need to look at the holistic systems, and we need to look at how we can integrate the full systems together using the linkages between the different 4 Ps that we established for sustainability here. And this gives us then a domain of addressing all the multi-criterias that happens within it here. And we need to establish the objectives, and we need to think of how we can blend them together. So this tailors us back into artificial intelligence and machine learning and building the algorithms in terms of the data mining and in terms of assemble models, to think of how each one of them is its own entity and it has its own matrix, and we need to actually align where the crossovers between these different elements are and how we can bring them together. And AI helps a lot in this element. Another element is to actually look at the life cycle analysis as a tool. And initially, life cycle analysis was all about understanding the system boundaries as a holistic system, looking at the cradle to grave element. And then that was enhanced to address cradle to cradle, which means one man's waste is another man's treasure or input, and then start addressing that. And then LCA has developed into the cost life cycle analysis, social life cycle analysis. So it starts integrating all these elements, and the whole essence or ethos of our research is to try and use these models to then build a holistic system here, to tailor make it for the chemical engineering, to focus on all the problems that link in science into engineering, into the useful products within a successful economy that encompasses the societal elements into it, while focusing on the biosphere element here. So we basically, essentially what we need to do is look at expanding the systems and generating a holistic chemical engineering endeavor that focuses on the entire concept of the 4 Ps as we established in sustainability element here. So that takes us into actually understanding that there is a fundamental link between what we refer to as the mesoscale, what happens in the lab, the microscale, what we do as unit operations in each one of the processes that we have, and then the whole industry or the whole process of manufacturing its elements here. And this helps us then break down what chemical engineering actually is. It's in everyday's life, from the time you wake up to the time you sleep. If you had medication, if you've done makeups, if you've done anything, transportations, energy, a chemical engineer must be involved in that process here. And we said it's all about the transformation of the raw material all the way to the useful products. But we need to link it between science and engineering. And in chemistry, they have the luxury of the periodic table. They choose any element they want. The cost is not an issue. 1 gram, 1,000 pounds is not a significant element to them. If the temperatures are 4,000 or 500 psi pressures, it's not. If it takes 5 hours or 6 hours to achieve an experiment, they are trying to prove a concept, while chemical engineers at the same time are trying to move from the concept into reality. I can't deal with materials that cost 1 gram, 1,000 pounds. I need 1,000 kilograms for 1 pound. My reverse of the economy causes an ambiguity for me. They use high temperatures and pressures. I need to think of how I can control the temperature and pressures, minimize the capital costs and the running costs that I have for energy, and then operate at the same performance level. At the same time, they want to prove a concept, so they generate the project at an infinite time, 5-6 hours for the process. In my case, when I wanted to generate ibuprofen pills, I need to generate 10,000 pills per minute as a successful endeavor to build a business element around it. So then I need to align what the chemists do between what we do as engineers. And there are several principles and several mechanisms. Green chemistry and environmental engineering, if you link them together, then that gives you a fundamental element of achieving the SDGs and sustainability in a whole processing element. So if we start thinking about the mesoscale all the way to the macro scale, that then gives us the 3 levels here between what the chemists do in a molecular level, what the global scale in a localized village that we have nowadays, where we have a logistics of supply chain, we have a global economy that impacts, we have resources, we have emissions issues, we have policy issues, and then chemical engineering at the process level sits as a linkage between what scientists are pushing the boundaries on and between the reality of logistics, transportations, emissions, all the other elements that we have to do here. So if chemical engineering sits here, it needs to link between the green chemistry at the molecular level, the mesoscale, and between the macro scale in the economical scales through the environmental engineering endeavors here. So the concept of the research that we set up at Southampton here is we need to align what the chemists do to then come up with a product design and then go into the sphere of how we can transform that product into reality, whether it's an existing product like ibuprofen or whether you're bringing new medication out of the system here, and essentially aligning everything together through the development, the formulations, the launch. And you need to encompass within that the macro scale of economy and legislations and all the other successful supply chain issues, and at the same time link it with the societal needs and the confinement of climate change and all the merging issues of waste generation and other things like that. So the whole holistic element is to look at the chemical transformation or industry as a hub that links between the fundamentals of sciences and between the requirements of reality in terms of economy and society and other things like that to bring the goods and help facilitate the functionality of life. So that takes us into what green chemistry are, and then align what the chemists are trying to do in a more sustainable manner. And green chemistry is essentially 12 principles that have been applied over the last 15 years to start thinking of the waste prevention and start thinking of the atom economy, when atom economy is all about what goes in must come out. That's the fundamental. Matter cannot be created nor destroyed. But when I look at a gram of carbon coming into a process, a gram of carbon will come out. Is it coming out at the product or is it coming out at the waste? And how can I convert it more towards the product rather than the waste here? And then addressing the hazards, looking at the alternative energies, looking at the societal elements in terms of using renewable energies or using efficient methods of energies, speeding up the reactions, applying advanced catalysis and other things like that. So it's about addressing the whole concept at the mesoscale element. And then when we start moving at the green engineering or sustainable engineering principles, again, it has a 12 principle element into it here, and they all come from the requirements of the product and the requirements of the process, and the whole essence between prevention and treatment, design for purification and separation, looking at conserving the complexity of the elements here and trying to reduce the chaos that aligns from the tail end of the process or the upfront of upscaling the raw material, and thinking about the durability and the requirements, minimizing, maximizing, integrating the elements of the whole process here and integrating all of them together. So it's an amalgamation between the mesoscale and the macro scale and how we can align these together here. And the concept behind it comes from the process itself. We have the raw material, we need to use it, we use it in our processing factories, that requires energies and waters, and then we generate goods and we generate waste. And the concept behind it is to actually reduce the feedstocks that we have, then reduce the emissions that we are generating, then reduce the demand on energy and water as much as we can, and then try and prevent waste. That's the first element that we do. The second element that we're trying to do here is to reuse some of the energies and some of the heats being generated, instead of being wasted, to be fed back into the process to minimize this element here. Then use the water sectors around this element here, then look at the waste streams that we're generating and think of how that waste stream could be actually fed into alternative processes and reused in a better manner here. And then look at the replacement elements of addressing, first of all, the feedstocks and moving towards the biological elements where they grow every 3-4 months, trying to understand the process of how can I transform complex elements like cellulose and linen into building blocks that come already from the other raw materials, and how I can capture this, reducing the footprints and other things like that here. Looking at the process itself and moving the process from large elements into smaller elements by intensifying, looking at the flow chemistry elements, looking at modularization, or new methodologies to start thinking of how we can process this element. And the last element of what we try to do is bring in innovations in terms of capturing the carbon, recycling the carbon, looking at the process, looking at inventing the new materials, and moving and aligning ourselves with the artificial intelligence to optimize and control the system in a more efficient manner. So the concept of the new research endeavor that we've done here is to actually look at the global problem and address all the aspects of it here, using the life cycle analysis as a complex system and expand the boundaries around it here. We started using multi-objectives and multi-criteria decision-making to come up with the ideal sustainable process, where we look at the different facets and the different criteria from the 4 Ps between the partnership, the planet, the profit, and people, and then what is important for us to maintain the success of the economy while minimizing the environmental damage, while maintaining societal needs, establishing this partnership between science at the fundamental levels and between the global logistic elements that we have to do here. And we've kind of started using advanced elements in terms of fuzzy logic and in terms of AHP and other successful systems that have been implemented. So we put up a working methodology, and when I say we, it started off with me as coming up with the research concept and building it, and now I have the success of 2 PhD students, another 3 starting in January, and at the moment we're running a campaign to try and raise some more funds. We're applying to some bodies here. So the concept that we came up with is look at data collections from the micro scale, from the macro scale, and understanding how the system boundaries happen on one side of the element, this side here, and then align that set of data to build up the criteria of the 4 Ps that we have here, and then establish the framework between the data mining and between the assemble models to build these artificial intelligent linkages to give us then an ability to go and simulate the processes with these decision criteria, to come up with different elements from them, to then establish the criteria of what the society need now and what the society need in the long term, what does the economy need, what does the planet planet need and how we can overcome it. And then we come up with the multi-criteria decision makings, and we start building these criteria around it to then align everything around the system, normalize it, do some sensitivity analysis, and come up with the real informed decisions to move the process plan forward. And then taking that generic methodology, we bring it down a bit further on, or we drill into it further on. So you can see here a snippet of the full system that we brought in. First of all, I have the chemistry-based analysis, where what are chemists doing and how they're applying the green chemistry, and what products and what processes they're thinking about establishing for ourselves here, and how we can adapt them to existing, historical, and future plans that we have to do here. And then start addressing the techno-economical elements, start looking at the life cycle analysis, start looking at the process analysis, start looking at the supply chain, to build up a set of criteria for ourselves within the 4 elements that the society requires for the success of the SDGs. And then once we establish the criteria, we need to break them down to sub-criteria and think of where the linkages between these sub-criteria and the top tier criteria are going to be, and then come up with a set of weighting to prioritize the sub-criteria and the criteria that we have here, then align them through different models that we have here to come up with the most informative decision we can establish. Because as we all know, when we address life happens between B and D, between the birth and the death, between cradle and grave, the concept of life cycle analysis. And between the B and the D, we are focusing on the C, the choice. And that's why we want to come up with the most informative process to generate a choice or a multi-criteria decision-making exercise to come up with then that choice or that decision from a sustainable point of view, to look at the long term and meet the goals of achieving today's current climate without compromising future generations' ability to establish themselves here. And we took the project at different levels. I first of all started off with the water, and I built up systems between looking at desalination, because certain areas around the world require water, and water is the source of life that we establish. And we looked at large endeavors around the planet, and we focused around the Middle East because that's where the water shortages are. And we looked at the large processing, and we tried to simulate new sustainable large processes. But then the question is, why do you want to go large when you can go small and modularized? And we looked at localization and looked at minimizing the quantity while meeting the needs. And that then gave us this modularity element of distributed water desalination to generate fresh waters based on locality of the demands and based on different elements. And then we build up these models between the economy, the society, the technical elements here, and we build these technical models to demonstrate that capability of rather than generating a large desalination element, that 3 million cubic meters of water, to generate us 50 cubic meters per day or 100 cubic meters per day, and then move that requirement of the small element to a renewable energy source and establish then a framework at a macro level in terms of a whole country like Oman or UAE requiring water, and then build that decision making to demonstrate that there is no need for a large endeavor, because you can do a small endeavor and many of them and still meet the economic success of water desalination, establishing the quantity of water you need in the region without the large capital expenditure, without the large emission levels here. Then we moved on to the building blocks of the society, of chemistry itself, and we looked at IPA or isopropyl as a chemical that we use in different elements of it here, and we build up different models and different systems about establishing factories, about looking at all the economic, the environmental, the social elements, the technical elements, and how we can align all of them together. And we established a new framework for this. And moving forward, as I said, from January onwards, I have 3 new PhD students starting. So we're going to start looking at the water food nexus element. And this is a project that I already started on. We've already modeled ammonia in terms of modularization, in terms of membranes, in terms of different technical abilities. So the student can come in and address the linkages from agriculture between the need for ammonia for fertilizers, the use of water, energy, and then the food demands globally, as a futuristic element 2030, 2050 and beyond that here. And then one of the new projects that we're going to look at is start addressing the circular economy, not just from an economic point of view, but also from a chemical point of view about the circularity of the chemicals and capturing and recycling some of the waste here. And the third project that I have is establishing the carbon capture and utilization and looking at the geothermal elements in terms of moving the reservoirs from hydrocarbon generation to actual hydrocarbon storages, but try to build successful models that will align us with minimizing the damages coming from emissions back into the reservoirs. Because at the moment, the down failure of carbon capture, carbon sequestration, all these elements here is the lack of a good economic model to justify profitability of the system here. We also have some ambition in terms of, at the moment, applying for 650,000 with UKRI research institutes to try and generate money to look at the biosystems as part of the energy systems here and establish a full framework. Now, my chemical engineering department sits within the School of Chemistry, and we have strong links with pharmaceutical companies. So we're trying to generate some funds to look at how the pharmaceutical industry can be transformed as well in terms of an ambitious design for a sustainable future here. There are many facets of what we're trying to establish here in my research group, and we at the moment are expanding. We're generating a few outputs here that I'm happy to share with Dr. Alam. We have new projects coming on site, and we're hoping to generate more income to sustain the future of the research. So if anyone has any questions about my research or about chemical engineering or the University of Southampton, what we're trying to do in terms of the micro to macro scale, please feel free to communicate with me at any stage here. I'm sorry I've rushed through the presentation, but I appreciate time is of the essence for everyone at the moment, and we're running out of time.